Hello, my name is Jack Montoya, and this is Physics 2211, Lab 3, the Black Hole Lab. Here is the timeline for my discussion of this lab. We will get started with the introduction. This lab is entirely computational, and it contains two parts. The first part involves observing a star's motion around a black hole in order to find the mass of that black hole. And then the second part is a ship leaving a planet orbiting the black hole, and the goal is to find a velocity for the ship to move toward the black hole but be able to escape its attraction force. Before we can get into the computational models, we need to look at some of the fundamental principles. Some important concepts to understand is that the perpendicular force, or the perpendicular rate of change of momentum, causes a change in direction of motion, while the parallel force, or parallel rate of change of momentum, changes the speed of motion. Another thing is that gravitation is a non-constant force, which means that when we use V average in our equations, we can assume that V average is V final. The equations we will be adding into the computational models from left to right will be the position update formula, the velocity update formula, the gravitational formula for force, and the equations for parallel and perpendicular force slash rate of change of momentum. To start with the computational model for part 1, I put my GT user email as the seed for the random trajectory of the star, and then initially we have the star's mass given in the problem and the time given as well. Then we can find momentum using the mass of the star times the velocity for both initial and final, and then delta V and delta P are both the change in velocity and change in momentum respectively. And dp dt refers to the change in momentum over the change in time, which is also equal to the force by Newton's second law. Lastly, we can manipulate the gravitational force equation to find that the mass of the black hole will be in terms of the net force as well as the star's mass and the distance between the black hole, which is at the origin, and the position of the star at any given point. This will give us various values for the black hole mass at each position that the star is at. Here are a few screenshots from my model. As you can see, the arrows represent the various forces, including the perpendicular, the parallel, and the net force. And we can see that the forces do change as the position of the star changes, and that we get a slightly different masses for the black hole at each of these positions. So if we take the average of all of those masses at each position, we get a mass of about 1.24 times 10 to the 34 kilograms for the black hole. In part 2, we use the mass of the black hole that we found from part 1, and now we can use the gravitational force equations to compute all the forces on the planet, both from the black hole and from the ship, as well as all the forces on the ship from the black hole and from the planet. And then we can use the velocity update and position update for the planet and the ship to track their trajectories in the model. Here's some screenshots from my model, and I found that this speed in the x and y component for the ship was best to get close to the black hole without getting sucked in or crashing into the planet. And with both parts of the computational model complete, these were my final results for this lab. While rate of change of momentum and net force have the same mathematical definition, they do usually interpret differently, as rate of change of momentum looks at motion while net force looks at all the forces summed together. And if the ship wanted to orbit the black hole, I get a speed of around this, which is more in the direction of the planet's motion instead of toward the black hole. Thank you.